This problem is what's known as a curve sketching problem. And what we're going to try to do is we're going to try to graph this function, x over x squared minus 4, using the calculator as little as possible and relying just on the things that we've learned previously, like increasing and decreasing intervals and relative extrema, concavity, points of inflection, etc. The things that we can find by hand to sketch this function. Without relying so much on a calculator. So as we begin, let's first of all remember, what is it that we're expected to know about a function or be able to find for a function? Well, these can be broken down into algebra things and calculus things. So the domain list and range and x and y intercepts and asymptotes list falls under the algebra category, where the more recent things that we've been covering, like critical values and extrema, etc., are kind of fall under that calculus list there. So these problems, I'll admit, are typically pretty long. So just for the sake of time for this video, I've sped through a lot of these and have pre-written a lot of things just so we can make it through in a reasonable amount of time. So first of all, the algebra things I just went ahead and wrote all out. I'll just mention each very briefly. The domain is pretty clear. It's going to be any x other than 2 or negative 2, because those x's you're not allowed to plug in because it would give you division by 0. So matter of fact, let's just jump down to vertical asymptotes. You would actually have a vertical asymptote at 2 and negative 2 due to that division by 0. The range is all real numbers. You don't necessarily have to see that one. That one you'll see kind of played out as we find the rest of the calculus information. But you can kind of tell as you approach any asymptote, oftentimes one side will approach infinity and one side will approach negative infinity, which is what's going to happen here. The x-intercept you can get by setting the function equal to 0. And so if you set this guy equal to 0, the only place this would be 0 is if the numerator was 0. So 0, 0 is the x-intercept. And on the other hand, if you want the y-intercept, you'll let the x be 0, in which case you also get 0, 0. So the x and the y-intercept match. They're at the origin. We already talked about the vertical asymptotes, and the horizontal asymptotes would be at y equals 0. This is where the function levels off as the x's get larger or tend towards infinity or negative infinity. You can see since the degree of the denominator is larger, it becomes what I call bottom heavy. The denominator is so much dominant over the numerator, it winds up being closer to 0, the fraction as a whole. So it tends to 0. So I went ahead and took the liberty of putting in everything that we know so far. We have a vertical asymptote at negative 2 and 2. We have a horizontal asymptote at the x-axis, or y equals 0. And we have the x and y intercepts listed here. So that just kind of speeds things along. And we can kind of see the main structure of the function. Now we just have some details to fill in, which is what calculus will help us do. So obviously the first calculus thing we need to do is take a derivative, because that leads to everything else. Critical values, extrema, etc., etc. So this guy's derivative, I think we need the quotient rule to do this. So let's just take it pretty slowly. We'd have x squared minus 4 times 1, that's the derivative of x, minus x times the derivative of x squared minus 4, which would be 2x, all divided by x squared minus 4 quantity squared. This will simplify, I believe, to, if you look at the numerator, x squared, here I'll just jot this real quickly here, x squared minus 4 minus 2x squared. Now the x squared and the minus 2x squared would give you a negative x squared. And you also have a minus 4. So if you pull that negative out of both terms, it'll be x squared plus 4. All divided by x squared minus 4 quantity squared right there. All right, so next step, once we have our first derivative, now we need critical values. So a critical value, you could attain a critical value where the derivative equals 0, or the derivative is undefined. Now the only place, let's just go ahead and handle that situation first. The only place I see this derivative undefined would be at plus or minus 2. That would give you division by 0. But I remember plus or minus 2 wasn't even in my domain. So there'll be interesting points to keep in mind, but I'm not going to call them critical values necessarily, because even though the derivative is undefined there, they can't be a max or a min because the original function wasn't even defined there. So I really think all I have to do is set this function equal to 0. Now basic algebra says that if you have a fraction equal to 0, the only way that can happen is if the numerator is equal to 0. So I see that this guy is not ever equal to 0. Negative quantity x squared plus 4. You can try setting it equal to 0, but you won't get any solutions. So this guy has no critical values. So that's pretty interesting. Okay, so next thing I'm going to do is I'm going to make up a number line, and I need to see what's going on with this function as far as it being increasing or decreasing. Now normally on my number line I would put all my critical values. Now I don't have any here, but I also have to remember to put on my number line anywhere where there's a discontinuity, because any break in the graph, you need to test points before and after those asymptotes or whatever they may be, just to be on the safe side. So I'll pick a point before negative 2, maybe like negative 3, between negative 2 and 2, maybe like 0, and after 2, maybe a point like 3. I'll take these, I'll plug them in the derivative. Now there's actually something kind of interesting about this derivative here. Here, let me erase some of this stuff here. If you look at this derivative, you'll notice that it's always the same regardless of the x you plug in, because you always have a negative times a positive, x squared plus 4 is always positive, divided by a positive, because when you square a quantity, it's going to be positive. So a negative times a positive divided by a positive, that's going to be negative any which way you look at it. So all three of these are negative, indicating that the function is decreasing as a negative slope, decreasing again after negative 2 because it's got a negative slope, and decreasing after positive 2 because it has a negative slope. So it's very peculiar. Normally they change increasing to decreasing or whatnot, but here all three places are decreasing. Okay, now that immediately shows me I don't have any extrema. There's no maxes or mins, so I'll keep plugging along. No relative maxes and mins, that is. Right. Now, simply for time's sake, because this took me a while, I went ahead and took the second derivative. Don't be surprised if this takes you upwards of 5 minutes or more to do the second derivative. But here's the first derivative right here. To take this second derivative, you would actually have to use the quotient rule, but just go slowly and carefully with your algebra. And when you simplify it, it should be the same thing as what I got, which is this right here. All right, now the function can only change concavity if it passes through 0. And so one thing I'm going to do is I'm going to set it equal to 0, just as because that could be a point of inflection. A point of inflection is a place where the function changes concavity. So if you look at this fraction here and you set the numerator equal to 0, you see that only has a solution at x equals 0. This expression here, that can never be 0 because it's x squared plus 12. You could try, but you'll see that's never 0. So x equals 0 is an interesting place we should look at. As well as, let's not forget, minus 2 and 2, because we've got vertical asymptotes there. So I need to test points in between all of these, because it could change concavity over an asymptote or over one of these places where the second derivative is 0. So we'll try f double prime at negative 3, for instance, negative 1, maybe 1, and maybe 3. Now let's take advantage of just basic arithmetic as best we can. We're not going to be looking for specific numerical values. Some observations I'm making right off the bat is the fact that x squared plus 12, that's always positive. And 2x, that could change sign, or x squared minus 4 cubed could change sign. We just have to be careful. So let's try plugging in -3. We would get 2 times -3, that's a negative, times a positive, which is always positive, like I said, divided by a positive. Because -3 cubed is 9, 9 minus 4 is 5, 5 cubed is certainly positive. Now, this net result is a negative quantity, indicating back here where this test point is, the function is concave down. Pardon my abbreviation, CD will just abbreviate concave down. If we plug in -1, we'll get a negative times a positive divided by a negative. Net result, positive, indicating the function is concave up there. At 1, you'd have a positive times a positive divided by a negative. Right? Positive times a positive times divided by a negative. Net result is a negative, indicating it's concave down. And after 2, how about 3? You get a positive times a positive divided by a positive, indicating it's concave up. So we have these different points of inflection. So these guys would all be considered POIs for short, points of inflection, indicating that the function changes from concave up to concave down at those particular places. So we're going to try to combine everything that we just learned into a fairly accurate graph. Okay, so I've already got the basic structure of the graph from the algebra information. Now here comes the increasing and decreasing and those sorts of things. So it's decreasing everywhere. Now let's think about before -2. How can you be decreasing back here, hug this horizontal asymptote, hug this vertical asymptote, while at the same time being concave down? Let's think about that. Hopefully you said something kind of like this. Does that look decreasing, concave down, and hug the appropriate asymptotes? It does. Okay, how about between -2 and 0? Well, in the whole interval (-2 to 2), it's going to be decreasing. But specifically on -2 to 0 is concave up, decreasing, and 0 to 2 is concave down, decreasing. So I think the only way to do that would be to be decreasing concave up and then decreasing concave down, like that. And then after 2, it looks like we're still decreasing forever, but in a concave up kind of way, right? Decreasing with a concave up type of way, and hug this vertical asymptote and hug this horizontal asymptote. The only way I think you could do that would be right here. Now, could you be down here potentially? Am I just picking one option of a lot of correct options? I don't think so, because if you were to draw the graph down here, that would be increasing, not decreasing. Right, so you'd have to be careful how you drew this. And it would be concave down, by the way, and it's supposed to be concave up. Okay, so there you go. This right here should be a somewhat accurate sketch of this function here. Now notice we didn't pay a whole lot of attention to exact y values at certain places or anything like that, but I think this would be more than sufficient just as a generic sketch of this very complicated function. So in summary, you can see how algebra combined with increasing and decreasing intervals and extrema, which this guy didn't necessarily have any relative extrema, and concavity and points of inflection can all be combined to give a pretty good graph of the function. So I'll tell you what, in closing, let me do this. I'll pull up my TI here, and let's see how we did. So I went ahead and took the liberty of plugging this guy in, x divided by x squared minus 4. And so if we push graph, we get a function kind of like this, which I'll cut out. Give me just a second. All right, let's paste it in here. Okay, blow it up a little bit. Right, and how did we do? Is that a pretty good, accurate depiction of the actual graph? Yeah, I think we did a fantastic job. And notice we did all of our work with no calculator. Everything was done by hand. So it's always good to use the calculator just to verify our answer. But it's always good to apply these new things that we're learning, like extrema and increasing and decreasing intervals, concavity, and that sort of stuff.